Hello and welcome to Erudite. In today's video we're going to be looking at the basics of the k nearest neighbours algorithm. All the code will be posted on GitHub and a link will be in the description. So let's get started. So to begin with, we're going to need some data. So let's draw a graph. We'll put our axes in, and then we'll add our numbers, and we're going to be looking at data about eggs. Oh, we can't forget our labels. And we'll add a bit of data in. There we go. And this red data, well, it's from a chicken, and our blue data from a quail. Now you can see that the quail's eggs are typically smaller in both the diameter and height, and the chicken's eggs are typically larger in diameter and height. And we're going to use the k nearest neighbours algorithm to predict whether an unknown point, which I'll show here as white, is either a chicken's egg or a quail's egg. But how are we going to do this? Well, let's have a look at some steps. And the first thing we're going to want to have to do is measure the distance from our unknown point, this white point, to all of the other points that we know, both the chicken and the quail. Now, how are we going to measure that distance? Well, let's first consider just 2 points, and we want to know the distance between these 2 points, and we're going to call that distance C for now. And what we're going to use is something called a Euclidean distance measurement. Don't worry, it's not complicated. We just take the 2 points which have their Cartesian coordinates x1, y1 and x2, y2, and we're going to construct a triangle where the base of that triangle is x2 minus x1 and the height, or the vertical component of that triangle, is y2 minus y1. And we can see in this triangle that C is our hypotenuse. And in school, we learnt a very handy formula or theorem for working out the hypotenuse, which was the Pythagorean theorem, where c squared is equal to a squared plus b squared, where a and b are the other two sides of this triangle. So if we take the square root of both sides of the Pythagorean theorem, we can rearrange it to give us just c, and that's what we wanted all along. And what we can do is substitute into this equation our known values of a and b, that x2 minus x1 and that y2 minus y1. And that gives us a really nice little equation for working out the Euclidean distance, or distance between these points, in 2 dimensions. But we can go even better than that, because we can generalize this equation. We can say that for n dimensions, we just add an extra term for each additional dimension. So if we had a z dimension, we would just add a z2 minus z1 squared into our sum before we did the square root operation. So we found a really nice formula for working out the Euclidean distance. Now I should just mention briefly that at high dimensions, the Euclidean distance stops being a useful way of measuring the relationship between data points, and that's for some quite in-depth reasons that we might explore in a future video, but for now this works perfectly. So how would we code this formula up? Well, there's a nice little function here that I've written up, and we can just have a look and work our way through it to understand what's happening. The first thing is just a little comment which shows us that the points, they've got to be passed as a list of x, y, z and so on of those Cartesian coordinates. So basically you just add an extra comma in for every dimension that you want to have in your point. And we pass to this function 2 points, point 1 and point 2, that we want to measure the distance between them. Now this first bit, it's just checking that the points are of the same dimension. because if they're different lengths, we can't do this calculation. So all it'll do is, if they're not the same length, it'll return none and print a little warning about the arrays not being compatible. And that's just a helpful little diagnostic if we ever hit any problems with this. So let's get to the more important chunk, which is this part here. So this is where we actually implement that calculation. We start with s is equal to 0, and then we iterate through and add each of these green terms into s. So s is effectively that sum before we carry out the square root operation. And then we just return here the square root operation of that s value. And in Python, 2 asterisks just means something raised to a power or to an index. So if we use the power of 0.5, it's the same as taking the square root of s. So now we've got the tools to measure the distances. And there we go. We're getting all our distances. So what do we do next? Well, we need to select the k number of points with the shortest distance. And this is where the k of k nearest neighbours comes in. What that is it's the number of neighbours that you want to use to characterise an unknown point. So in this instance we're going to take 3, and that's a bit arbitrary. But in a future video I'm going to show how we can actually calculate or determine an optimal k value. But let's just stick with k being 3 for now, and we'll select the 3 shortest distances. And there we can see we've got our 3 shortest distances to those 3 points. So now we just count up the outputs for these points, and we can see there's 2 chicken and 1 quail, and you can see it's very obvious what we're going to do next. We use the mode function, and mode just gives the most common value in a list or in an array. So we use mode to predict the unknown output, and of course it's going to predict that this value's a chicken or a chicken egg. And that's spot on. Now I wonder if you can see what would happen if we had used k equal to 5 instead. And we'll have a look at that in just a second. So now we've seen the basics of how the k nearest neighbours algorithm works, let's implement it in Python. I've got here a simple import of statistics, and that comes with Python, you don't have to install it, and we're only going to use mode from that. And we've got our little defined Euclidean distance function, and I've just minimised it. That's what the 3 dots in that little yellow box are showing. There's extra lines, but I've minimised it so we can fit everything into this nice little template. And what we're going to do is we're going to start by looking at what needs to go into our k nearest neighbours function. The first thing we're going to pass to it is the query, our unknown point, with its x, y, z values. Then we're going to want to pass our known inputs, that's the x and y values, say for that egg example, of things we knew what they were, so whether they were chicken or quail. And they go together with our known outputs. So the known inputs is the size, say the diameter and the height, and the known output is whether it's a chicken egg or a quail egg. And they're really important because they're how we test our query value. And then we want our k number, that number of neighbours that we're going to use to determine what our unknown, our query value is, or predict what our query value is. And the first thing we're going to do, once we've got all of that, is we're going to measure the distances between our query point and our known points. And you can see this little one-liner, it's just a piece of list comprehension. And all we do is we set a list equal to distances, and in that list we use our Euclidean distance function to measure the distance between our query point and each point in our known inputs. We just iterate them using P for P in known inputs. So it just iterates through each one of those, giving me a distance. So now we have our distances, and that's fantastic. What do we do with them next? Well, we need to select the k number of shortest distances. So in our example, that was 3. So what we do is I start by initializing this list, placing just a set of zeros for the k number we need. So it'd be 3 zeros in this case. And then we have a placeholder, and don't worry about that, we'll come back to why that's important in a second. But for I in range of our k number, so until we get to 3, we're going to keep running this loop where we find the minimum distance in our distance set, and we want the index of that distance. And we take that index and we look in our known outputs at that index position, and we add that to our shortest list, because what it does is it tells us whether that short distance is for a chicken egg or for a quail egg. So we're starting to populate that shortest with those outputs. And then what we do is we set that distance equal to the greatest distance, to the max distance, because if we didn't do that, every time we cycled this loop, it would just keep picking out the same minimum distance. And I've just put a little print statement in there so that we can see what's in our shortest. So now we have that shortest set that has either chicken egg or quail egg in it, and we use mode, we use that statistics function just to find out which is the most common value in our shortest, and that is our output. So in our example, chicken egg was the most common because there were 2 of those and only 1 of quail egg, so it outputted chicken egg, and that was the prediction. So let's just minimize this function, and we'll look at it with the example that we did before as a data query. So you can see here that I've got the inputs as a 2D array with height and diameter, and the outputs for quail and chicken, where quail is 1 and chicken is 2. Chicken egg, sorry, is 2. And we've got our test point, our unknown point of 39 and 29, so 39mm height and 29mm diameter. And we're going to pass that into our KNN function, our test point with our known inputs, known outputs, and we're going to use 3 as our k value. And let's see what happens in the terminal. So it printed the list that we had of 2, 2 and 1, so 2 chicken eggs and 1 quail egg, they were the closest distances. So our KNN algorithm predicts that our unknown point would be a chicken egg. But what happens if we set the k value to 5? Let's run that in the terminal. You can see that it's now changed its prediction, because it's saying, okay, well there's 2 chicken egg values close, but there's 3 quail egg values close. So actually I'm now predicting it's a quail egg. And this is a weakness of the k nearest neighbours algorithm, that number of neighbours, especially on boundary positions between data, can have a big influence on how an unknown point is assigned. Now, I think we've looked at the basics of the KNN algorithm. We've implemented it really nicely here with a really simple, straightforward function. I think that's where I'm going to leave this today, but we haven't finished with this topic, because in a future video I want to explore higher dimensional data and also methods that we can test the validity of the KNN algorithm prediction, because it's all well and good as having that predicted value, but we need to know how accurate and how useful that piece of information is.